Good afternoon, everyone. My name is Dongpen Xu. I'm now an assistant professor in the computer science department in the University of New Hampshire. This is the work I did in my last year of my PhD. So it is about detection of virtualized code. I'm very happy to be here to share with you some of the insights and the experiences in this research. Okay, so let's get started. So the first is I will give you a brief introduction of what code virtualization is. So the virtualization here is quite different from the virtualization like in VMware, those system level virtualization. So the code virtualization here is actually a translation procedure. It will translate a binary code, for example, in x86 platform to another new instruction set, for example, a RISC machine. It could be a real computer like a RISC machine, or it can be an imaginary virtual CPU. So before the input of a code virtualization is a binary code like in x86, the output of virtualization is a program which contains two parts. First, a set of virtual instructions, and a simulator, which can interpret these virtual instructions. So it's kind of translate a program into an equivalent program. So by nature, code virtualization can be used for code obfuscation or program protection. So there are many obfuscation tools in industry like code virtualizer here. It can translate x86 code to virtual instructions. As a technique, the code virtualization has some good points and bad points. So first, the advantage is it is super certificated. It is very hard to reverse engineer the virtualized code. And also, the variety is good. There are many ways to design VMs. So even if one VM is hacked or is cracked by a super smart hacker, it can be but the program protected by other VMs are still safe. And the third one is like the virtualization can be easily incorporated or can be easily integrated with other obfuscations. For example, control flow obfuscations or opaque predicate. You can implement those other obfuscations on the virtual machines. But on the other hand, the drawback of code virtualization is like, number one, it is the performance. Think about it. Every x86 instruction will be translated to a virtual instruction and will be interpreted during runtime. There will be lots of performance loss. And also the second drawback is the compatibility. Not all instruction in the x86 platform can be translated to a virtual machine. And also, for some program structure, it is not easy to correctly translate it to the virtual instruction. For example, it has a very complicated control flow or the exception handler. Those things are not easy to translate to virtual machine instruction set. So, based on those pros and cons of code virtualization, in the manual of, typically this is the guideline in the user manual of the virtualization tools like the code virtualizer. The first guideline is like only virtualize the important piece of code. For example, if you are a software developer, you can virtualize the trial and registration check part. That is the important part. You don't want your program to be that part to be reverse engineered. And also, you may want to virtualize the encryption, the initialize of the encryption key part. So only virtualize the small part of the program. And the second guideline is do not apply virtualization to a loop, especially when the loop will iterate like multiple times, thousands of times. That will cause performance loss. And the third guideline is do not apply virtualization to some complicated program structures, for example, the exception handler or switch statement. So think about it. Actually, what you can apply virtualization is not a big program. So you can only, there's less opportunity for you to apply virtualization. That's the current stage of virtualization. Actually, only a small piece of code can be virtualized. Keep that in mind. On the other hand, there's an area called De-Virtualization, because security experts always are very curious about whether we can reverse engineer the semantics from this virtualized code. And it also has practical effect. For example, malware developer now, they are trying to use virtualized based tools to virtualize their code so that they can hide the signatures of their malware. So I summarize there are some existing work in this area. I summarize those work as 3 categories. So the first one is that they want to reverse the virtualizer by detect the dispatcher loop. So dispatching loop is a typical way to implement a virtualizer. Like it will fetch the opcode of the virtualized instructions, and based on different opcode, it will send it will call the different dispatcher to handle it. The second category is to for example, some virtual machine is very difficult to handle. You can work out this problem as a backward way. So what you want to care is the piece of code that affects the program behavior. So you can backtrack from the program behavior so that you don't need to care about the details of the VM. The third category is a new angle. Maybe it's because the virtualized code is super complicated. So the authors are trying to generate a new program. This method is called program synthesis. They can generate a new program which is equivalent to the old program. Then, based on this new program, you can do the analysis so that you can ignore the complexity of the virtual machine. However, all of the existing work are based on a very strong assumption. That is, they already known where the virtualized code is. But this is not to find the where. I mean, based on my previous description, only a small piece of the code in the whole program can be virtualized. So identify this small piece of code is not trivial. I can show you an example. So this is in our observation, we run a virtualized malware. So the core part of the virtualized code is only 1,000 instructions. But the whole execution of the malware is 2 million of instructions. This is the runtime trace. So what we are doing is trying to find this 1,000 instruction among the 2 million of instructions. This is like we are searching for a needle in a haystack. This is totally not trivial. So in order to solve this problem, we propose our method called the VMHunt. So this project can identify and extract the virtualized code from an execution trace. And based on the information we get, we can further simplify the virtualized snippet and to get a so-called virtualized kernel. And last, we can translate this virtualized kernel to a formula and to verify whether to do some further analysis, and also to verify whether this formula is equivalent to the original program for other analysis. So here's a big picture of this research. So first, we start from a virtualized binary code. A piece of it is virtualized inside it. We run the whole program to get an execution trace. And then we are looking for a special instruction sequence called context switch instructions. So the white part is the normal native execution. The blue part is the context switch. Think about it. There is only a piece of it. A piece of the code inside it is virtualized. So during runtime, there must be a switch between the native code and the virtualized code. So we are trying to identify this context switch behavior. And then the code snippet between two context switch is the virtualized code. This is the red part. Then we can extract the red part. This is the virtualized snippet. But typically, the virtualized snippet is also very, very large. So we, based on the context information, we can go one step further to simplify this virtualized snippet to generate a kernel of the virtualized code. So this is the core part of the virtualized code. Then we do a specific symbolic execution called multi-granularity symbolic execution to translate the kernel to a formula for a verification or other analysis. So this is the high picture of the whole project. So the key point of this project is the context switch, the kernel extraction, and also the multi-granularity symbolic execution. So I will pay more attention to those three parts. First, context switch. In context, here in our scenario, the context means the values inside all the registers. So so the context switch actually did two things. First, save or restore the values inside the register, or swap the values in the register to memory, or swap the memory back to the registers. And the second is a jump instruction after the context switch behavior. So here is an example. This is the execution trace during runtime. So the blue part is the context switch behavior. Particularly the first blue part is called context save behavior. You can see that it push all the registers from the push all the values in the register to the memory, to the stack, and at the end of it, there's a jump instruction, jump to the starting point of the virtualized code. And the second part, similarly, it works in the opposite way. It pops all the values from the memory and to the register. So this is the context restore operation. At the end of the context restore, there's a jump instruction, jump back to the native program execution. So the area between the context save and the context restore operations are the virtualized snippet we are looking for. Then, because typically the virtualized snippet we get from between the two context switch instructions are still very large. The partial reason is that there are lots of other obfuscation techniques used in virtualization. So this snippet is still very large. So what we are doing, fortunately, the context switch operations provide us some hint to find more information about the virtualized code. So in this step, we can extract the kernel or the core part of that virtualized code. So here is an example. The blue part is where the context is saved on the stack. So this is the context, and the stack grows from up to down. The context here in the stack is an excellent delimiter to separate the stack area used by the native program and the VM program. So the green part is the stack area above the context is the area used by the native program, and the area below the context is the VM stack. The red part is the stack area that's used by the virtual machine during its store the local variables, maintains only local runtime, and the green area is the native code. So the native code uses the green area, and then there's a context switch. It will store all the context in the blue part, and then the VM only use the red part. But there are only two scenarios or two situations that the VM will write some data back to the blue part and the green part, and that behavior is exactly what we are looking for. That means at the end of the virtual machine execution, it will write the result of this virtualized code execution to the native program so that the native program can reuse those results afterwards. Therefore, we are trying to, so we backward slice from the two operations. One operation is to, like in the virtualized code, you write some data to the blue part. That means it writes the data to the context. Those contexts will be restored after the virtualization code execution. So the native program can reuse it. The second category is to write the data to the green part. That is the native stack. Of course, after the virtualized code, the native program will continue execution based on the green part. That is the stack for the native program. So this is the what we can get from the what we can do more simplification given the information from the context. And after we get the execution kernel, we will do a symbolic execution called Multi-Gran symbolic execution to translate the program from instructions to a formula for further analysis and for verification. So I do not have time to go to very details of this technique. So here I just want to highlight several points. So this symbolic execution there are several features in this symbolic execution. So first, the length of the symbolic value and the concrete value can be various. It's not fixed. Like in traditional symbolic execution, there's only one length of the value, like 32 bits or some bit level or byte level. But in this symbolic execution, the length can be flexible, can be various. And the second is like the symbolic execution can interpret some instructions during the execution. And by these two features, our symbolic execution can produce more concise formulas. So I will quickly go through a simple example here to give you a quick picture of how this works. So first, this is a move instruction. Move the constant to a register EAX, and the result is shown on the right. And then we load a symbol. Typically, the data from memory is marked as a symbol. So we move the symbol from memory to the middle byte of the register. So typically, in this way, the traditional symbolic execution, they will mark the whole EAX as symbol. So in our symbolic execution, we can only mark the middle part as a symbol. And then there's a shift left operation, shift the whole EAX by 4 bits to the left. So our symbolic execution can simulate this operation. So we just directly move it, not generate a formula to move it. So this is what our symbolic execution engine can do. And at last, there's an AND instruction and a constant to the value in the EAX. So actually, at the end, after the AND operation, the symbol 1 here is cancelled by the AND operation. So the output of our execution, symbolic execution, can produce a constant value at last. But in traditional symbolic execution, there's only like a formula. They cannot tell you like at last that value is a constant. Okay, so far is the high level picture and the methods in the VMHunt project. So we also do some evaluation to evaluate this project. We try several open source programs, the real world open source programs, and we insert like a trial registration scheme into those open source projects, and we use modern virtualized tools like Code Virtualizer, ThemeMinder, and VM-Protect and ES-Encryptor to virtualize them. And at the end we use VMHunt to detect all of them. And because we already have the trial registration scheme, we can run symbolic execution on the trial registration scheme first and compare the formula we get here with the formula we get from the VMHunt. So this is a verifiable like simplification. So I mean, the result of VMHunt is verifiable. Another group of evaluation is about malware. So we get some malware from the VirtuTotal and some other forums, and we run VMHunt to analyze them. VMHunt can successfully detect the virtualized part of it. And we also have a case study about a ransomware called Tears. And here is the left part is here's some information about the Tears. So the left part is the virtualized snippet between two context switch instructions. We have a utility to recover the control flow graph from the trace. So this is all those control flow graphs are recovered from the trace. So the left part is the virtualized snippet between two context switches. So this is still very large, but the right part is the kernel. So only backtrack from the two write operations. So it can significantly simplify the virtualized code. Okay, so that's almost the most important thing in this research. As the takeaway message, so I want you to keep two things in your mind. So first is virtualize is not about the whole program. Usually virtualized obfuscation can only be used in a small piece of code in the in a whole program, and we propose a tool called VMHunt, and it can detect and simplify the virtualized code. And that's all. Okay, thank you very much.
Nice work, and it's good to meet you here.
Thank you. Good to meet you too.
So it's a quick question. So I can imagine there are thousands of ways to generate the context switch snippet. Do you have any comments on that?
Great question. Yeah, we have analysis to handle the various variety of context switch instructions. So we have a kind of a people optimizer to it keeps a sliding window, and to tackle some of the obfuscation during you can change the order or insert some junking instructions between the context switch instructions, right?
Yeah, I understand that. So in your example, they store the context on the stack.
Yeah.
What if I store them on the heap?
Also a good question. So that is I want to interpret this as in this way. So usually this is a binary instrument, the virtualizer. So using stack is safer than using heap. You do not need to assume the APIs, or you do not assume the memory allocation or memory management. Stack is very easy to use. So you just use the area below the virtualized the context part. That part is totally safe. But if you use heap, it is very hard to maybe cause the virtualized code to crack.
Yeah, that makes sense to me. Last question.
Yeah.
Do you have a plan to open source your tool?
Sure. Yeah.
Thank you.
Yeah, it will be online very soon.
Thank you. Oh, sorry.
Hi. I'd like to ask you a question. I have reversed some binaries that consist of multiple emulators, and in that case, so the context switch approach that you propose might not work that well, because you have many context switches and you don't know which context switch correspond to which VM. And
you mean there are multiple VMs, right?
Yeah, there are multiple VMs. So you have a context switch. So
Yes.
because in your approach, you get two context switches, and you assume that between these is emulate the virtualized code. But I have seen cases that there are multiple context switches. So between this context switch, you don't know the context switch to which VM corresponds to. So it's not trivial to extract and say, hey, this is the virtualized one.
That's a good.
So I was wondering whether you handle this, and second, how resistant your approach is, because how easy for me that I want to, for example, as a malware author, to insert bogus context switches and screw up your analysis.
As the first answer your first question, we have a matching procedure to match the context switch instructions. The hint is the steps of the stack. So for the context save instructions, it saved the context in somewhere in the stack. It can only be matched to the context save, context restore operation that restore the data from the same stack area. So that is the match with the like the context save and context restore operations. So that you can match the two part. And the different there could be multiple virtualized VM in one program execution trace. We treat them as different VMs. Yeah, but we just match the context save instructions with the context restore operations.
I see.
Yeah. The second question is if the malware developer know our analysis, how we can still...
I mean, like we can do like many tricks, like implement a stack in the heap or having a duplicate stack, writing at two memory locations at the same time. So writing to one, reading from the other. So you can do like many tricks to overcome this. And also then how resistant is your approach?
Yeah, I agree. Yeah. There's also like if they totally know how our system is implemented, I believe there's an opportunity to hack our system. I think but we do raise the bar for malware developer. So
yeah, it's definitely like a good work. But yeah,
and as I said, I want to share with you like the experience I got from this research. Like the virtualized code is only a small piece of it. So yeah.
Okay, thank you. Excellent work. And,
Thank you.
Sean Criswell, University of Rochester. So congratulations. I think you started a context switching arms race. So, so along those lines, one other thing you might want to consider is the fact that context switching can actually be interprocedural. Right? So for example, the Linux kernel, when it does context switching, there's actually certain registers it doesn't save because the calling convention of the C function already saved some of the registers on the stack. Right? So you could potentially have the case where some registers are saved in one function and then some other registers are saved in another function. So something else you might want to consider in your new arms race.
Okay. Yeah. Thank you. Thank you very much.
Because I don't want to keep you from lunch, which is next. Sorry, not lunch, dinner.
Okay, time flies.
Confused. First, let's thank Dongpeng again, and then some other words.